This lesson is about the central limit theorem for proportions. Consider the following example. It turns out that 34% of Americans have a college degree. We call that our population proportion, or P. Let's examine what a sampling distribution would mean and look like in a case like this. I want you to imagine that we were to take a random sample of 100 Americans. Here's my random sample of 100 Americans. You can see from the blue and orange here in my random sample that 42% of this random sample has a college degree. We call that sample proportion P hat, the hat indicating the little triangle thing that we write above the P to remind us that it is a sample proportion and not a population proportion. But wait, if 34% of Americans have a college degree, is it possible that I could take a random sample and 42% of them would have a college degree? Well, that absolutely is possible because samples vary. I could plot that 42% on my sampling distribution here and continue. So what if I took another sample, random sample of 100 Americans? What if this time, as you can see from the blue and orange people here, what if this time only 25% of the sample had a college degree? Is it possible that from a population of 34% college graduates, that a sample could have only 25% college graduates? Again, that's absolutely possible, as samples vary. I could plot my 25% on my distribution here. Suppose I took a third random sample of 100 Americans, and this time 34% of the sample had a college degree, just like 34% of the population. I could plot that here on my distribution. And because samples vary, I could take another sample and another sample and get a different sample proportion each time, despite the fact that each time these samples were chosen from a large population which had 34% college graduates. Suppose I were to continue to take random samples of 100 people over and over, and each time plotting the proportion that had a college degree. If I did this enough times, I might get something that looks like this. So, what does the central limit theorem for proportions tell us about the sampling distribution? Well, the central limit theorem for proportions is essentially three statements. Statement 1. Before I get to statement 1, the central limit theorem requires that we check that the sample size times the yes percentage and the sample size times the no percentage both are 5 or higher. Now in this case, if you do those multiplications, you'll get numbers much greater than 5, therefore that checks out in this case. And if both of those calculations are greater than or equal to 5, which they are here, the central limit theorem makes 3 predictions. Prediction 1. Our sampling distribution will be normally distributed. Prediction 2. The average of my sampling distribution will be the same as my population proportion. Now this average has a lengthy name, and so we tend to call it mu p hat, reminding us that it is the average of sample proportions. Prediction 3. The central limit theorem gives us a way to calculate the standard deviation of the sampling distribution, which I'll get to in a minute. This standard deviation of sampling distribution has a lengthy name, so we like to denote it as sigma p hat, reminding us that it is the standard deviation of population proportions. And further, the central limit theorem gives us a way to calculate this 0.047 number. And here is the way we calculate it. Notice inside this radical, I have my yes percentage times my no percentage divided by my sample size. Okay, so let's generalize. In general, if a certain percentage of my population, say P, has a certain characteristic, and I were to look at a sampling distribution for a certain sample size, call it n, as long as these two calculations are both greater than or equal to 5, the central limit theorem states, 1, my sampling distribution will be normally distributed. It will have an average equal to the population proportion, and it will have a standard deviation that can be calculated as shown. And that concludes the lesson.